Friends, let's draw the shear force and bending moment diagram for a given beam having uniformly distributed load. So if you look at here, we have got a beam AB which is simply supported at point A and point B. At point A we have got a hinge support, at point B we have got roller support. And there is a uniformly distributed load of intensity 50 newtons per meter is acting on the beam over the entire span length of 4 meter. So now we have to draw shear force and bending moment diagram for this particular beam. So this is a case of an uniformly distributed load acting on a simply supported beam, and we have to draw shear force diagram and bending moment diagram for this particular condition. So friends, if you want to draw shear force and bending moment diagram for this particular beam, we have to first draw the free body diagram and we have to find the support reactions acting at point A and point B. So friends, let's start with the step 1. To draw free body diagram of this particular system. As we are aware friends, in free body diagram we remove the supports and we show only force acting on the body. For example, on this particular beam there are two supports, right? So we'll be removing these two supports at point A and point B, and at the place of these supports we shall be providing the support reaction, that is forces acting at point A and point B. So let's draw the free body diagram as a first step. So if you look at here, this is the free body diagram friends. So at point A we have got support reaction over here. So let me call this support reaction as RA, and here at point B we got another support reaction, that is RB. So with the help of this free body diagram, what we do, we calculate the support reaction at point A and point B, and that is our step 1. So that is to find the support reaction. So here we have support reaction, that is RA and RB. We shall be calculating RA and RB over here. Now in order to find the support reaction, we are going to use the condition of static equilibrium. We know that the condition of static equilibrium, that is the summation of vertical forces equal to 0, means all the vertical forces acting on this particular beam must be balanced. Next we have summation of horizontal forces. So summation of f of x, that is all the horizontal forces acting on the beam are balanced. And the next condition is all the moments of forces acting on the beam are balanced. So we can take moment of force about any point you can take. So I can take about point A, let's say. So moment of forces acting on the beam about point A is going to be balanced, that is summation of m of A equal to 0. So these are the conditions which are called as condition of static equilibrium. Now we are aware that here there is no horizontal force acting on the beam. So this particular condition will be ruled out. So we shall be considering only this condition, that is all the vertical forces are balanced and all the moments acting on the beam are balanced. So we'll proceed with these two conditions and let's see what we get. So I'm going to first follow summation of vertical forces are balanced. That means I'm going to use by condition summation of forces in the vertical direction, y is considered as vertical forces equal to 0. So that would give you, see, this is the upward force and this is also upward force. So both are I'm going to consider positive. So RA is positive because acting upward, and RB is also positive because it is also acting upward direction. Now this uniformly distributed load which is acting from point A to B having intensity 50 newtons per meter can be converted into point load. So this is an equivalent point load, we can say. So 50 into distance is 4, so that is going to be 200 newtons. So that 200 newton is going to act somewhere here at the center, which is going to be acting at the center of span, that is 2 meters, like this friends. Okay, so now I'll not be considering this uniformly distributed load, rather its equivalent load, which is a point load 200 newton, which is at the center of span length 4 meter. So now I'm going to only consider this load. So it is acting downward friends, so it is going to be minus, so minus 200 equals 0. Please remember this is upward, so I have taken it positive. This is also upward, so I have taken it as positive. This is downward, so that is why I have taken it as negative as per sign convention. So if I simplify this, I'll be getting RA plus RB equals 200 newtons. So this you can call as equation 1. So we shall use it whenever we require it. Okay. So first condition I have utilized, that is summation of vertical forces are balanced. Now I'm going to take second condition, the moment of forces about any point of the beam is going to be balanced. Okay, so that is I'm going to use this second condition. Also by using condition summation of moment of forces, here I am considering point A. You can take any point, you can take point B also. Moment of forces about point A is going to be 0. So from here, if you see, this RA is acting at the same point A. So it will not cause any kind of moment or rotation of the beam. So the moment caused by this RA is going to be 0 because distance of this particular force from point A is going to be 0. So so that I will not take. The second force is this, which is equivalent point load of this uniformly distributed loading. So this is 200 newtons into a distance 2 meter from point A. So 200 into 2. So I'm going to write 200 into 2. And please remember, because of application of this point load, your beam shall rotate in the clockwise sense like this. Okay. So clockwise we are considering positive. Okay. This is I am taking as positive, while anti-clockwise rotation I am considering as negative. So following this simple sign convention, I can say that this is going to be clockwise. So this is positive, friends. So plus 200 into 2. Now this whole uniformly distributed load is being taken care by this point load. Okay. So this moment 200 into 2 we have written already. Now the remaining force is RB, which is acting at point B at distance 4 meter from point A. So we can say that this force will rotate the beam in the anti-clockwise direction, something like this. Okay. So it will be RB into 4 meter but negative. So minus RB times 4 meters, and as you know that this is anti-clockwise rotation, this is going to be negative, friends, and that whole ends up equal to 0. And if I simplify this, it's very simple calculation. So 200 into 2 is going to be 400, and 400 equals, you'll be getting 4 times RB. So RB is going to be, friends, very straightforward, 400 divided by 4, and therefore you'll be getting RB equals 100 newtons. So this is going to be equation 2. So we got value of RB, friends. And if I substitute value of RB in the equation 1, so we have RA plus RB equal to 200. Therefore RA will be what? 200 minus RB. RB is 100. So we'll be getting RA equals 100 newtons. So by simple calculation, we could easily find out the support reaction at A and support reaction at B. That is RA equal to 100 newtons and RB equal to 100 newtons. So in step 1, we have found out the reaction at point A and the reaction at point B. So friends, we got reaction at this particular point, that is RA, as 100 newtons. Okay. And similarly, we also got the reaction at point B, that is RB, and that is also equal to 100 newtons. So in step 2, we will draw the shear force diagram. So in order to draw the shear force diagram, we will be calculating shear forces at various points of the beam. So we would like to calculate the shear forces at various points along the length of the beam. Now here, if you see, from point A to B, there is a uniformly distributed load acting over the entire span length of the beam, and there is no other force coming between point A and B, only the uniformly distributed load is acting from point A to B. So it means the shear force will be varying according to the variation of uniformly distributed load. Now if you see that at every point, as we move from point A to point B, at every point the value of load is going to change. It means there will be variation of shear force from point A to B, which is according to the variation of uniformly distributed load over the entire span length of the beam. So we will have to consider each and every point over the length of the beam in order to find out the variation of shear forces. Because as we move from point A to point B, at every point the amount of load is going to increase. In order to draw shear force diagram, when there is a uniformly distributed load is given between point A and B, what we do is we take a section at certain point. So we will be considering a section somewhere like this. We are considering a section XX, so which is a distance, let's say from point A, this distance is going to be X. So we have considered a section XX at distance X from point A. We will find out the shear force at this particular section. If you want to find shear force at this particular section, friends, so at this particular section, the effective load will be this much of uniformly distributed load, which is this much portion, friends. So this much portion of uniformly distributed load is going to cause a shear force at section XX. So what I will do, I will convert this uniformly distributed load into a point load. If I convert this much uniformly distributed load into point load, it is going to be load intensity, that is 50 times the distance is X. So now as we move this particular plane towards right, accordingly the X is going to change, and accordingly what happens at that particular section, shear force is going to change. So let us say that shear force at section XX. So now I'm going to write shear force at section XX as SF. So I'm going to call SFX. Now if you look at here, if you take this particular plane, this reaction RA is acting upward. So this will cause a positive shear. Okay. So this will be positive shear. This RA is going to cause positive shear at this particular plane. So it is plus 100, and then this is 50 into X, which is the effect of this much uniformly distributed load is acting downward. So downward shear we are taken as negative, so minus 50 into X. So this is basically shear force acting at section XX. As I am going to shift this particular plane towards right, the value of x is going to change, and accordingly the value of shear force at that particular location will change. So that is what we got, friends. So we got shear force at any plane at distance x is given as 100 minus 50x. Okay, this is positive because shear force is acting upward, and this is negative because shear force is acting downward. So in order to draw the variation of shear forces from point A to point B, we should take number of points along the length of the beam. So for our convenience, we will be taking in between, we'll be considering 4 points because the span length is 4. So it will be easy for us to consider 4 points. So I'm going to take 4 points in between. So let's say I'm going to consider this particular point here. Another point is here, friends. The next point is here. At this particular point, let's say this point I'm going to call C. This point I'm calling as D. This point I'm calling as E. Okay, and last point is B. So at C, x is equal to, let's say at point C, x equal to 1. At D, x equal to 2, friends, because it is in center. And at E, x equal to what? X equal to 3. So like that, x equal to 0. At this particular point, we'll have x equal to 1. At D, we'll have x equal to 2. At E, we'll have x equal to 3, friends. And at B, we'll have x equal to 4. So like that, I am going to consider 1, 2, 3, 4, 5 points over the entire length of the beam. So let's write down. So we have x over here, friends, and corresponding to x, we'll have shear force at particular plane, shear force at distance x. So shear force at distance x is given as 100 minus 50x, friends. Now we will have point A. So point A corresponds to x equal to 0. Okay. Well, at this particular point, the distance x is going to be 0 because this section would be coming at point A. Similarly, we'll have for point C, x is going to be equal to 1. Similarly, point D. At point D, we'll have x equal to 2. At point E, friends, x will be equal to 3. And at point B, that last point, that is this point, friends, x is going to be equal to 4. So when I put x equal to 0 in this particular expression, which is 100 minus 50x, you'll get shear force at point A, that is shear force at point A will be equal to 100 minus 0, that is going to be 100. Now then we'll have at point C, friends, so shear force at point C. At point C we'll have x equal to 1, so we put x equal to 1, so 100 minus 50 into 1, so it is going to be 50 only. Okay, 50 newtons. We will have shear force at point D similarly. So at point D, x value is going to be 2. So it is 100 minus 50 into 2, that is 0. So for D, x equal to 2. So if you substitute value of x equal to 2, you will get 100 minus 50 into 2, that is 100 minus 100. So this value is going to be 0 newtons. And similarly for E, if you go for E, x is going to be 3. So you will be getting 100 minus 50 into 3, that is 150. So value would come as minus 50. Now at last point, friends, shear force at point B. So when you do shear force at point B, x value is going to be 4. So 100 minus 4 into 50, that is 100 minus 200, that is going to be minus 100. So if you see here, your shear force at point A was 100, then it becomes 50 at point C, and then at point D it becomes 0, and then at point E it becomes minus 50, and again at point B it became 0. So it is varying like this. Okay, now if you look at here, shear force is changing with x, and variation of shear force with x is linear variation because this is single degree curve. Okay, so all these variations are going to be straight line. Please remember, because this is a linear variation, friends. This indicates the linear variation because shear force at any section is equal to 100 minus 50 into x. So this is a linear variation. So for linear variation, we will have a straight line graph. Okay, please remember. So this is the linear variation, friends. So let me plot these shear forces corresponding to all these points. So let's see how it looks like. We'll be plotting shear force variation along this line. This I'm going to call as shear force diagram. So now if you see here, the shear force at this particular point. So here if you see that the uniformly distributed load is starting from here. So I can take a section just before point A. So if you take just before point A, there is no force acting just before A, friends. Therefore the shear force just before point A is going to be 0. So we have got, friends, shear force just before point A is going to be 0, and the shear force just after point A if you take. So shear force at a plane just after point A is going to include this particular force, that is 100 Newton upward. So this is going to be plus. So I will say this is plus 100 Newtons. So plus. Okay. Now if I want to find shear force at point C, so it is a distance x equal to 1 meter. So we got shear force at point C is 50 Newtons. Okay, this is the point C, friends. So it is somewhere here, maybe somewhere here, friends, 50 Newtons. And similarly shear force at point D, which is here at center, is going to be 0. So this is going to be 0, friends. Okay, so we got a variation like this, friends. So it varies. It goes from 0 Newton to 100 Newton at point A. Just before A it is 0, just after A it is 100, and from A to D it goes to 100 to 0. Okay. Now if I want to find shear force at point A, it is minus 50. So it is going to be minus 50 here, and shear force at point B is minus 100 newtons. So now I can plot the variation. Okay, let's see how it looks like. So as you can see that the shear force goes from 0 to 100 newtons like this, and then it goes from 100 to 0 over here till point D, from 0 to minus 100. Okay, and now as you cross the point B, like if you put your section somewhere here, so this minus 100 which was here, now this also will be included. Just left it was minus 100, it was coming. So if you cross this particular section, then this minus 100, then you'll have plus RB is going to come into the picture. So minus 100 plus 100 is going to be 0. That we are going to get 0 over here, friends. So 0 newtons. Okay, so it goes from 100 to 0 at this particular point. Okay, so this particular graph represents the variation of shear forces along the length of the beam due to application of uniformly distributed load. So this is also called a shear force diagram. Now similarly, now in the step 3 we will take the same beam and we'll try to draw the variation of bending moments. Okay, and from there we will be able to get the bending moment diagram. So let's go for step 3. So in the step 3, friends, we would like to draw the bending moment diagram. So for that, we'll first calculate the bending moments at various points. Since from point A to B there is only uniformly distributed load acting, so we can consider a section, let's say XX, like this, at distance x from point A. So we can find out the bending moment at this particular section, and as we move the section from point A to B, we can find the variation of bending moments along the length of the beam at various points. So first we'll calculate the bending moment at this particular section XX. The bending moment at distance x from point A is given as bending moment at x. Okay, so if you want to find the bending moment at this particular point, so your beam is going to bend something like this, friends. Okay, so this is called as sagging of the beam. Okay, so due to support reaction Ra, your beam will bend in this fashion. So this is the example of sagging of the beam, friends. So you will have bending moment at this particular section xx as Ra into this distance, which is going to be x. So that is going to be, friends, Ra means 100 into x, and that is positive here because your beam is bending like this. It is sagging, friends, so it is going to be positive. Now if you take this particular section, this much uniformly distributed load is coming into the picture. So if I convert this uniformly distributed load into point load, so it will be something like this. So the intensity is 50, so 50 into x will be 50x. This is the point load equivalent of the uniformly distributed load, and it is going to act at a distance from here to here is x by 2, because this is always going to act at the center at the midpoint of the length. So this length is going to be x, so it is going to act at distance x by 2. This is going to be x by 2. So this particular load, which is due to uniformly distributed load, will cause the hogging of the beam like this. Okay, this is going to be negative. So 50x into this distance, which is again x by 2. This is also x by 2, friends. 50 into x, that is force, into the distances from here to here is again, friends, x by 2. So into x by 2. The negative indicates your beam is bending like this, which is hogging. Okay, so if I simplify this, so you'll be getting expression for bending moment at section x as Bm x equals 100x minus 50 by 2 x square, or we can simplify it as 100x minus 25x square. So this is the expression of bending moment at various points of the beam from point A to B. Okay, so now if I substitute the value of x, I can find out the bending moment at various points along the length of the beam. So let's do it, friends. So I'm going to take again the value of x as 1 meter, then center line 2 meter, then 3 meter and 4 meter, like that I'm going to do. So friends, we'll have x, and then we'll have bending moment at corresponding points on the beam. Okay, which is given by an expression of 100x minus 25x square. So the first point is A. So at A we have x equal to 0, friends. Then I can take another point somewhere here, a point at the center, and then here this point I'll call as C, this I'll be calling as D, and this I'm going to call as E. So at C x equal to 1, friends, at D x equal to 2, at E x equal to 3, and again B x equal to 4, like that. Okay, so we'll have x equal to 0, then we have C x equal to 1, D will have, friends, x equal to 2, E x equals 3, and then last one is the B again, where you have x equal to 4. So now we'll substitute the corresponding values of x in the expression. So bending moment at point A is going to be, now if I put x equal to 0, the whole value is going to be 0. So when I put x equal to 1, that is bending moment at point C, so we'll have 100 into 1 minus 25, and that is going to be 75 Newton meter. Okay, 100 into 1, 100, 25 into 1, so 100 minus 25. Now we'll have x equal to 2. So bending moment at point B, friends, that is going to be 100 into 2, that is 200, and then 25 into 4, so 200 minus 100, that is going to be 100 again Newton meter. Again I am repeating, 100 into 2, because x value is 2, so 200, and 25 into 4, 2 square is 4, so 25 into 4 is going to be 100, so 200 minus 100 is going to be 100. Now we'll have bending moment at point E. So here it is going to be 3, friends. So 100 into 3 is going to be 300, and 3 square is going to be 9. So 9 into 25. So if I write here, it is going to be 100 into 3 minus 25 into 3 square is 9. So if you simplify this, it is going to be 300 minus 225. So 300 minus 225 is going to be 75, friends. So this is going to come as 75 Newton meter. And then again we'll have bending moment at point B, that is last point over here. So now I'm going to put x equal to 4, so 100 into 4 in this expression, minus 25 into 4 square. So this value 100 into 4 is going to 400, and this is going to be 400. This is going to 0 Newton meter. Okay. Now just to get proper variation, we have taken 4 points. You can take more than 4 points. Okay. You can divide beam into 8 part also. So x equal to, you can take 0.5, then 1, then 1.5, like that also you can divide, you'll get a variation. Okay, so as far as this particular example is concerned, I think dividing beam into 4 points are sufficient. So now we got bending moments at various points. Now we'll plot that bending moment along the length of the beam. Let me show you how we can plot it. So we have drawn the vertical grid lines corresponding to each point we have taken. Okay, like this. So this is basically we call as bending moment diagram, because I am going to represent the bending moment variation. Okay, so now we'll be starting from point A. So at point A, bending moment is going to be 0, like this. At point C, bending moment is 75 Newton meters. Okay, at point C, this particular point, friends, we have bending moment as 75. So let's say it is 75 somewhere here. Okay, please remember the variation of bending moment with respect to x is the second degree curve. This is second degree curve, friends, because it is coming in the form of x square. Okay, so it is going to be a graph like this. Okay, now next, so here at point D, the bending moment is something 100 Newton meters. Now when you go to point E, this is point E, friends. So point E, we got it as 75 again. So we are getting 75 here, friends, 75 Newton meter. And again at point B, it is coming as 0 Newton meter. So it is 0 Newton meter. So it is starting from 0 Newton meter. At point A, it goes to 75, and then it is coming back to 75, and then becoming 0. If I plot the graph, it will be looking like this. It is second degree curve, friends. Okay, something like this it will be varying. Okay, so this is very important to remember here. This is second degree curve. Okay, now this indicates the variation of bending moment along the length of the beam due to application of uniformly distributed load. So you can see here, so it goes from 0 Newton meter to 100 Newton meter, and then again comes back to 0 Newton meter. Okay, this diagram is called as bending moment diagram. So we are able to draw shear force diagram as well as bending moment diagram for the given beam which is subjected to a uniformly distributed load of intensity 15 Newton per meter. Thank you very much.